Good morning, students. Uh, See, we have completed these five topics in our unit 2. Today, we are going to start the sixth topic, that is extended surfaces and fins. Now, I am moving to the slide. So, here we are going to look at this extended surfaces or fins. Okay. See, in the reality, if this is your wall, we are drawing a wall here. So whatever the heat transfer that is happening from this wall to the atmosphere is limited by this area. Whatever the area that is present here, okay, that area is area with which fluid is interacting. Okay, area with which fluid is interacting. So this will be like the convection area available for the convection. So whatever the heat transfer that is happening between the wall and the surrounding air or the fluid is actually limited by this area. If I can increase the area here, the heat transfer by convection increases. Q is equal to H into A into T minus T infinity. We know this by Newton's law of cooling. That is law governing convection. Okay, this is Newton's law of cooling and this is the law governing convection. If I want to increase the heat transfer by convection, if I can increase my A, it is very simple way of increasing my Q. So how I go about and do it? Okay, how can I increase the area? For that purpose, I will have something called as extended surface or the fence. Okay, it is extended surface, or this is also called as fence. So whatever the wall that is there here for me previously, this wall will have a fin now. Okay, that is I'm extending its surface. Okay, so this is how your fin will look like. Now what happened previously, you used to have only this much of area available for convection here. Area available for convection previously. Okay, previously, instead of writing previously without fin, if I write, it will be more appropriate. Without fin, this is the area available. Now you look at what happened. The area available has increased. Okay, it has increased. Area on the top, area on the bottom, and this area on sides, and this area that was existing previously. So along with this area, you got a lot of area added to this. So now what happens? Q is equal to HA delta T. We know this, T minus T infinity. Now you have increased the area, obviously heat transfer will increase. Okay. See, in many of the applications, you wanted to increase the heat transfer. Okay. For example, let me take the IC engine concept itself. Okay. You have studied a lot about IC engines in your thermal engineering. Okay. This is how IC engine will look like. Okay. I'm showing a piston here. This is a cylinder, outside one, and this is a piston, and then connecting rod, crank, and the crankshaft. Okay, this will be rotating like this. This is how it will be like. And whatever the heat that is produced here due to the chemical reaction, this heat should be immediately taken out. Okay, it has to be immediately taken out. You don't want it to be there. Okay, you want to take it out immediately, taken out. So to take out this area, there are various ways of taking out the heat. You know something called as water cooling and air cooling. Okay, water cooling is a one concept, and here air cooling will help us. Okay, air cooling, what you will do is you will increase the surface area that is available on the cylinder outer surface by adding fins. Okay, you will add so many fins like this. You have added a fin here, you have added a fin here. Like this, you keep on adding the fins, you will increase the surface area. Whenever the surface area is increased, the heat transfer by convection is increased, and whatever the heat that is present inside will be taken at a faster rate. Okay. Previously, it will go only at lesser rate. Now the rate of heat transfer to the atmosphere from the cylinder gases will increase because of the increase in surface area that is available here. Again, not only here, this particular concept can be used, okay, as I have said here, it will be used in IC engine concept. It can be used in evaporator coils or radiator. Okay, core radiator, you can see. You can have it in computer parts. Okay, that is computer cooling also. You will use the fins. Okay, likewise, many examples can be given here. Okay, so I'm showing some figures to you here. Okay, here you can see the various you know fins that are there for a IC engine. Okay, on an engine, so many fins are there. Why fins are there here? Because you wanted to take out the heat that is present inside, and that is the reason why people have placed these fins over here. Okay, this is one important application of these fins. Okay, you must have seen this radiator. Okay, this radiator fins will have so many uh, fins will be placed here, and that will increase the surface area of this tube. Okay, so that the interaction with the air is increased and the heat transfer to the air is increased. And then this is the evaporator coil. Okay, where you will get the evaporator? Evaporator you will use in your air conditioners and in your refrigerators. You will be using this evaporator coils. Okay, these evaporators I have so many pins here. As you can see, you have extended the surface of this one. The surface area available for convection we have increased even in this case. Okay, even in the PC cooling also this is used. Okay, as you can see, this is a one typical example where you will have different kinds of fins here. In the bottom, you can see the fins are of one kind. Whatever the heat that is there in the microprocessor, it has to be taken out immediately. Okay, so all our electronics, the computers, the cell phones, basically they work on the microprocessors. Okay, this microprocessor, the disadvantage is they produce a lot of heat, and that heat should be taken out. How you will take out the heat? Using the fins, you have to take out the heat. Okay, so this is a one complex configuration wherein heat is being taken out of the you know microprocessor or the electronic part. Okay, this is a very simple way of doing the heat transfer. Okay, but this one is a complex way. The previous one that I have shown is a complex way of dealing with the heat. Okay, so this particular application of electronics will have huge potential for you to work with, because what happens is various electronic companies are booming up, and because of that, what happens is like you will have a lot of scope to work in this area. People want to actually cool their electronics at a faster rate, let it be TV or let it be um, cell phone, let it be any given electronic item, nobody wants lot of heating. So for that, what you have to do, you have to take away the heat from the microprocessor. To take away the heat from the microprocessor, what you have to do, you have to use the concept of fins and install the appropriate number of fins with an appropriate design, that can, perform with a better cooling rate. Okay, so that's how the fins can be used in computer cooling and in various applications altogether. Okay, now let us move to our particular concept. Okay, let us take the diagram once again here. Okay, let me draw it again here. This is my wall. This is my wall here. On this wall, I'm attaching a fin here. Okay, this is how your fin will look like. This is the fin. This red color part is fin, and the blue color part is your wall. Now what I have to do, I have to do the mathematical modeling of this part. So how do I do this mathematical modeling? For this purpose, what I'll do is, I'll consider a small element here, a small element here, like this, okay, of small thickness. We'll consider, okay, simply put, it is this. Okay, it is there throughout. And the small element, I'm drawing it here. Okay, I'm drawing an exaggerated view of it here. And then taking this element, I will be understanding how the heat transfer is happening in my domain. See, when the heat transfer is happening through the solid, it is heat transfer by conduction. Within the solid, it is a heat transfer by conduction. So Q conduction is entering here. Let me call it as X. On the other side, it is leaving. This will also be Q conduction, which is represented with X plus dx. Okay, like we have done for our conduction case in the first unit. Okay, so this is Q conduction X, and this is Q conduction X plus dx that is going out. And along with that, there will be something called as Q convection that is also coming out throughout. Okay, so I have to take the conduction that is entering and leaving, and also the convection that is coming out of it has to be considered. Okay, if I have to write the conservation of this thing here, the expression will be like this. The expression is like rate of heat conduction into the element. What is the element? The simple element that I have considered here, that element I am speaking about. Into the element yet x. Okay, this is on your entry side. This will be equal to the sum of this one. Okay, that is the rate of heat conduction out of the element yet delta x. Okay, meaning this part is your delta x. Okay, Okay, this is delta x, right? So this is the conduction thing. Conduction thing is over. So what is left out is your convection now. What is convection? Rate of heat convection. See how this convection is happening? This convection will happen throughout. Okay, it will happen on this side. Okay, it will happen on this side, and at the bottom. That is, it is happening throughout the perimeter. Rate of heat convection along its perimeter. That has to be considered here. So what I have done is I have taken this, let me call this as 1, this as 2, this as 3. So this will become 1, this will become 2, and this will become 3. It's like that. Okay, so that's what I've done basically. So if I have to write it in simple terms, so Q conduction at X will be equal to Q conduction at X plus dx plus Q convection I will have. Okay. Now, what I do, I take the conduction on one side. So what I do is Q conduction X minus Q conduction X plus dx. So what I'm doing is essentially I'm taking the conduction x plus dx onto my left hand side. On the other side, I will have convection left out. Okay. This convection, what I'll do is I will write it as, what is the formula for convection? It is HA delta T. It is T minus T infinity. So if I take A here, what will be my A? Tell me. Which you have to see in A, one dimension, it is delta x. Okay. If I have to consider the remaining dimension is this one. Okay. What is this? This is nothing but your perimeter. Okay. This is nothing but your perimeter. Okay. So this is perimeter. So the area will be that P into delta x. So H into P into delta x into T minus T infinity you will get. Okay. That's how you are getting the Q convection side. On this side, what I have is Q conduction x minus Q conduction x plus dx by, what I'll do is I will write the delta x that is present here onto my left hand side so that it will get divided by. So what I left out with on this side is HP into T minus T infinity, right? So that is your Q on the numerator and delta x on the denominator. So what I got essentially is, it is nothing but dq by dx, simply put. Okay, derivative of q with respect to x I got on the left hand side. So that's why I have transformed it this way. To get this differential only, I have transformed it this way. See, if you look at this q conduction, it is coming out. Okay, since it is coming out, it will be more compared to the q conduction that is entering. So this has to be negative because this value is big value and this is a small value. So small minus big will yield you a negative. So to make that negative positive, I have introduced a negative here again. So that's how you got this dq by dx here. But what is this q here? What is this q? Q, according to your Fourier's law of heat conduction, it is minus Ka dt by dx. So what I'm doing is essentially I'm trying to convert this Q in terms of T. Okay. If I do this, as per your Fourier's law of heat conduction, Q is equal to minus Ka dt by dx. So I have substituted it in place of my P. On the right hand side, I'll leave it as it is. Now, K and A, this K and A is constant value. The thermal conductivity is a constant, and then area is constant value. So you can take them out of your differentiation, and what you get is minus into minus, you'll get plus. So d square T by dx square you will get. And this will be equal to the Ka I have taken out, and I will write it here on my right hand side. And I'll divide that Ka on the right hand side. So this is how you got the expression. Now what I'll do is I will consider two things here. What I'll do is I will write T minus T infinity equal to theta. So that T minus T infinity, I will equate it with theta. And also I will write that Hp by Ka, I will equate it with m square, some constant m square. Okay, this is an assumption. The use of this assumption you will understand as we go ahead. So now take it for granted. So theta is T minus T infinity. That is one assumption. The other assumption is Hp by Ka. I will take it as m square. Then what I'll do is I will substitute these things into this one. So what I'll do is I'll call this as A maybe. Yeah. So this is B and C. Substitute B and C in A. Then what I get is, see, T infinity is a constant and T is a variable. So if I differentiate this with respect to T, what I get is, if you take, I'll do it aside here, theta is equal to T minus T infinity. If I do dt by dx, it will be simply dt by dx. If I differentiate it again, d square theta by dx square is equal to d square T by dx square. So what I got on my left hand side is actually d square T by dx square, and on my right hand side what I got is, in place of Hp by Ka I got m square, and in place of T minus T infinity I got theta. Okay, so this we will use later. For now let me use theta itself here. Okay, why I'm using theta here you will understand. See, if you look at this equation, what kind of differential equation is this? Somebody please speak out. There are types of differential equations, isn't it? For one kind of differential equation, you will have one way of finding a solution. So tell me, what is the kind of differential equation it is? It is a linear differential equation. Okay, if you have a linear differential equation, what is the solution for this? The general solution for this kind of thing will be theta is equal to C1 into e power mx plus C2 into e power minus m. General solution will look like. Okay, if you want to understand how did I get this general solution expression, you may have to refer to any mathematics textbooks wherein you will have this concept called as linear differential equations concept for finding a general solution of refer any mathematics textbooks wherein we have this differential equations. There, you go to the linear differential equation and you will have this. Can do that. Right. So moving on, what I should tell you the three important cases that we are going to be in case of a fin. Okay. In case of a fin, you will have three cases, and these three cases you must remember clearly because in a given problem, you have to first understand which case this particular problem belongs to. Okay. So these cases are very, very important. So give it a very good ear. So point is, first one is infinitely long fin. And the second case is short fin. And the third case is here short fin with tip insulation. Let me take without here, without insulation. And I'll take with insulation on with tip insulator. So these are the three cases. The first case is a long fin. The second case is short fin. Okay, this is the wall. This side it is insulated. Okay. And in the third case there is no insulation. Okay. It's a short fin, but the insulation is not present on the tip of the fin. Okay. That's how the three cases are like. Okay, if you take the first case, no, temperature at fin tip will be equal to the temperature of the atmosphere. That is, in reality, you cannot have this infinitely long fin. It is not infinite actually, but it is so long that whatever the temperature that is present at the tip of it, okay, temperature that is present at the tip of it has become equal to the temperature of the atmosphere that is prevailing around. That's how the first case is taken. And in most of the cases, in infinitely long fin case, what happens is your, let me write it here, length of the fin very much larger compared to the diameter of the fin. Okay, or the other dimension of the fin. This is the diameter dimension I'm speaking about. This is the length dimension I'm speaking about. Okay, this L will be very large compared to your other dimensions. Then you will call it as an infinitely long fin. Okay, short fin can be of small size. Okay, and in the short fin case itself, you will have two cases again here, one with the insulation and one without insulation. Okay. So these are the two cases that you are going to have here. Now, what I'll do is, I will take the infinitely long long fin case. I will take. Okay, if this is an infinitely long fin case, for the this governing equation and this general solution, this is a governing equation, and this is the general solution. For this governing equation and the given general solution, if I have infinitely long fin, I will have a given set of boundary conditions. Okay, that given set of boundary conditions I have to apply here. Okay, so if I take a thing here, it's so long, and the temperature that is prevailing here is equal to T infinity. And here I'll call the temperature as a base temperature, that is the temperature that is prevailing over the wall itself. Okay, that is a base temperature, I will call it. So this will be x is equal to 0, and this will be x is equal to L. Okay. So this is x is equal to L, but this x is equal to L can be called as x is equal to infinity here in this case, because it is a infinitely long sum. Since it is an infinitely long sum, what I can do is I can call that x is equal to infinity. If that is the case, so what I get is, yet x is equal to 0, I am getting a temperature which is equal to TB. Isn't it? And at x is equal to L, that is x is equal to infinity in our case. The temperature is different. It is T infinity. Okay. I hope it's clear to you. What we have done is essentially we have taken a Dirichlet boundary condition, that is temperature boundary condition on the both sides, and we will use this to solve the governing equation or the general solution that we have. What is the general solution we have? The general solution we have is theta is equal to C1 into e power mx plus C2 into e power minus mx. This is your governing equation, sorry, general solution. Now, into this, I have to substitute the boundary conditions. But this governing, this general solution is in the terms of theta. It is in the terms of theta. So, what I have to do is I have to convert my temperatures also in terms of theta. Okay. So, what is theta here? Theta is essentially T minus T infinity, what we have taken. So in this case, T is TB. Okay. So TB minus T infinity you get in the x is equal to 0 case. And in the next one, that is x is equal to infinity, T is equal to T minus T infinity, but T itself is T infinity, that is T infinity minus T infinity you will get here. So the theta will get 0 in the second case. Okay. So that's why this is the reason why we have actually considered this theta is equal to T minus T infinity, and also to get your linear differential equation in this form, we have considered that theta is equal to T minus T infinity actually. Anyways, what we get here is substitution of this one. So what shall I do? Let me call this as 1. This one is different from the one that I have used already. So I hope you will find it clearly. So what I will do is I will substitute 2 in 1. When I substitute 2 in 1, what I get is theta. Okay. Let me call this as theta naught, representing the theta that is at x is equal to 0. Okay. To clarify that, to differentiate that, I have taken this as theta naught. Okay. So when I substitute that, what I get is theta naught is equal to the x value is 0, C1 into e power 0 plus C2 into e power minus 0 you will get. So what it will give you, something power 0 is 1. So what you get is theta naught is equal to C1 plus C2 you will get. Okay. This is how you will get the theta naught. And then what I do is I substitute 3 in 1. When I substitute 3 in 1, I will get theta on this side. In place of x, I will be getting infinity. So if this is the case, what will happen to your Basically, this theta is 0 in this case. That's why. This is 0 essentially. Okay. That's how we got it. And then from this, if you look at, okay, this whole term will become 0 because it is power minus infinity is 0. So this whole term will turn out to be 0. When this is turning out to be 0, this C1 into e power plus mx cannot be 0. So C1 will be 0. So what I can say is from this, if I use this one C1 and this expression here, from these two, what I can write as C2 will be equal to theta naught. So C1 is 0 and C2 is theta naught. That's what I will get. Let me call this as 4. Call this as 5. Now what I'll do is I'll substitute 4 and 5 in 1. When I do that, what happens is this C1 will become 0 here. This C1 will become 0. The C2 value, I'll get it as theta naught. So if I do that, what I get is theta is equal to 0 plus theta naught into e power minus mx. So essentially what I got is theta by theta naught is equal to e power minus mx. Theta by theta naught. What is theta? Theta is t minus t infinity. I got it our assumption. Theta naught what it is? It is tb minus t infinity. That is equal to e power minus mx. Okay. So this is what we got. That is the temperature variation. Okay, it is like the previous thing only that we have done for slab, cylinder, the composite slab, composite cylinder, and composite sphere. What we have done, the same thing we are doing here, but only the difference is the variation of the temperature there, it's different. Here, it's different. Here, it is exponential temperature variation. Okay, this question can be asked in competitive exams. If fin is there, okay, for fin, he'll give you A, B, C, D. Okay, this kind of questions can be asked, like the straight line variation or the linear variation is the first one, and the second one is your logarithmic, parabolic, and then exponential. Okay, the exponential will be the right. If you know this concept, you can answer the question. Okay. So we will conclude this here for today.